Well, hello everybody. Welcome back. This is Prof. K, and welcome to Unit 4 on severe weather. This is the blood and guts of the course as we get into the forms of severe weather that cause damage. And today we are focusing on the garden variety thunderstorm cell. Just like the cell in biology is one of the most important concepts. So the thunderstorm cell is an important concept in meteorology, and we want to cover it today in detail. As you can see, we're going to review some of the conditions that support thunderstorms. Why do I say review? Because this goes back to prior to the midterm when we were looking at moisture and precipitation and atmospheric stability. We're going to go back and review some of those things. And the life cycle of a thunderstorm cell. We'll go through what the typical thunderstorm cell does during its life cycle. The phase changes of water substance that we see in a thunderstorm, what outflow boundaries are, and how thunderstorms can happen where we least expect them. And finally, we will spend the last period of time looking at lightning and thunder. And we'll wind up with some information on lightning safety, and that will be very important for you to know. Well, here is a cumulonimbus cloud. You know about them from our session on clouds. The biggest cloud goes all the way to the tropopause, and you can see where the tropopause is, where the cloud spreads out like an anvil at the top. That's where the tropopause is. So what are the conditions that support thunderstorms? Well, first of all, we have to have unstable air. And that can happen in one or both of two ways. Either very warm air near the surface, and of course warmer air rises, and you know the rest, Reckhecker, or very cold air near the tropopause. That produces a very steep environmental lapse rate and enables parcels of air to rise quickly. Or you can have both. Both and would be the best. Also, abundant moisture. Moisture is water vapor. Water vapor, when it condenses, it releases energy. And this can happen in a couple of ways. A low-level jet, usually around 850 millibars, brings a fresh supply of water vapor in from perhaps a water source, like the Gulf of Mexico or the Atlantic Ocean. Upper level moisture, shown as milky on water vapor image. And in some extreme cases, an atmospheric river, which focuses moisture into a line of thunderstorms and is a direct connection to the tropics. How about surface convergence? We know about convergence. Convergence happens when air is forced together. And of course, when air is forced together, at the surface, there is nowhere to go but up. And then at an outflow boundary, and you don't know what an outflow boundary is yet, we will be spending some significant time on outflow boundaries in just a few minutes. Finally, at the tropopause level, we can have divergence going on. Divergence near the tropopause, that is air that is spreading apart or accelerating, and you know already about jet streaks. Right entrance, left exit quadrants of jet streaks are especially good for divergence, and air rises from underneath. The more of these things that are present in the atmosphere, the more likely it is that we will have thunderstorms. Remember nudge and judge? This is just a review of our atmospheric stability lecture back in Unit 2. Here we have an environmental lapse rate that is quite steep, and parcels of air will continue to rise because as they rise, their temperature is warmer than the environment, and they keep going up. This may be helpful to go back and review this. You've seen it before, but this will become important again as we talk about thunderstorms. We can have instability above the surface. Air near the surface is stable. And as it rises, maybe it's forced to rise, because it won't rise by itself. So it's forced to rise by a cold front, or maybe a mountain, and it reaches a certain level and the air becomes unstable. This is called elevated instability, and I am posting a sample case study that I did myself called From Fog to Hail in 5 Minutes. And I would like you to take a look at this because it's a good example of elevated instability and how you can have some very bizarre and interesting weather combinations, fog and hail, happening at the same time. Remember this? Lots of lean, weather may be mean. Time to bring that back again as we take a look at instability in the atmosphere. So ELR number 1, the environmental lapse rate number 1, is the most unstable because it's leaning over the most. Finally, this sounding Little Rock, Arkansas shows the 3 indicators that we look at. We look at lifted index, is it negative? We look at totals index, is it above 50? And we look at the CAPE, convectively available potential energy, greater than 1,000. And all of those things together will produce conditions that are favorable for thunderstorms. This is all review of our atmospheric stability lecture, but we're bringing all this back as we talk about thunderstorms. Oh no, here we are again. The Holy Grail slide. You knew that you were going to see this again, and we need to bring it back because in a typical thunderstorm cell, all of the phase changes in this diagram are found. So let's look at the dynamics of a mature thunderstorm cell. Here's a graphic that shows a side view of a thunderstorm cell. It's moving from left to right, and you can see by the arrows that there is an updraft coming in from the front and moving up to the tropopause, and then there's a downdraft coming down toward the ground. And that downdraft reaches the ground, has to go somewhere, and so it goes forward as what is called a gust front. So, stage 1. Stage 1 of a thunderstorm, as it goes through its evolutionary cycle, is the updraft stage. The air is unstable, it rises on its own, and all the heat liberating processes are engaged here. There's condensation, there's deposition at high elevations where it's cold, there's freezing that goes on. All of these things are heat liberating processes in the updraft. Stage 2 is where the downdraft forms. And as the downdraft forms, we have to understand that it starts to rain out of the upper reaches of the thunderstorm, and as the raindrops fall out of the upper part of the cloud, some of them evaporate. And evaporation is a heat absorbing process. Some of the snowflakes, the Bergeron snowflakes that form in the upper part of the cloud, those snowflakes disappear into water vapor. Sublimation is a heat absorbing process. Melting of snowflakes into raindrops is a heat absorbing process. And all of this takes its energy from the air surrounding. And so the air becomes rain cooled. Cool air sinks, and even though it warms by Shishadek, it still arrives at the surface cooler than the surroundings. And so just like you pour syrup on pancakes, the syrup goes out in all directions. So rain-cooled air drops down to the surface and then goes in all directions as a gust front. Finally, stage 3. Stage 3 is where the updraft ceases and all you have is the downdraft. And the downdraft smothers the updraft and the cell finally dies. So I like to think of stage 3 as like one of those holiday ornaments, like a snowman that has a hot air fan inside to keep it inflated. When you turn off the hot air fan, the whole thing just kind of collapses down to the ground. And this whole process lasts about an hour. So thunderstorm cells go up, do their thing, and die in about 1 hour. But you say, Prof. K, wait a minute. Thunderstorm lines seem to last for hours at a time. How can that be? Well, as we will find out more in one of our future lectures, we know that lines of thunderstorms are made up of cells that come and go. Some of them are going and some of them are growing. And so what looks to be one line is really a series of cells that are coming and going. Here's another illustration of the energy changes that go on through the phase changes of water substance, and I'll leave that to you to look at. Well, what are outflow boundaries? Well, we said that outflow boundaries are gust fronts that happen when the downdraft reaches the ground, can't go anywhere else but out. And so as the downdraft reaches the ground, it goes out and becomes what I like to call a mesoscale cold front. It's colder air than the surroundings. And so the cold front then wedges itself underneath warm, humid air ahead of the thunderstorm. So it moves out ahead. Well, when two outflow boundaries collide, things happen. And so let's take a look at some examples of outflow boundaries. First of all, here is a radar image of a thunderstorm, actually a couple of thunderstorm cells that were growing up over Nuckolls County, Nebraska. And you can see surrounding the thunderstorm cell, you see the outflow boundary. And if you were actually living in one of those areas where the boundary was going through, you would experience kind of a little chill in the air. And overhead, you would see some clouds, not big clouds, but just some cumulus clouds. And that's what shows up on the radar. But let's see what happens when you have two cells that produce outflow boundaries. In this case, we have two adjacent cells, each producing a boundary, and the arrow is pointing to a third cell in its very earliest stage of development. Why is it there? Well, why it's there? Because the two outflow boundaries are combining and forcing air to rise, and that produces a separate updraft and a new thunderstorm cell. We can follow this process over a period of about an hour. This happens to be on the east coast of Florida. We have Cape Canaveral up here near the top of the image. And at 4:40 p.m. local time, we have a thunderstorm cell located inland from the Atlantic Ocean producing an outflow boundary. And there is a line of cumulus clouds, and this is produced by the sea breeze that's coming in from the Atlantic Ocean. And we talked about sea breezes back when we talked about local weather. And so hot air over the land is rising and producing these cumulus clouds. As we go from 440 to 451 on the upper right, we see that the outflow boundary begins to interact with the sea breeze front. And at 5:09 p.m., a new thunderstorm cell with some pretty violent weather is going up where those two boundaries meet. Meanwhile, the original thunderstorm is disappearing. Its life cycle is now almost over. And at 5:38 p.m., just 58 minutes after the whole thing began, our thunderstorm is very much in progress, where the two boundaries meet. and our original thunderstorm is completely gone. So outflow boundaries play a huge role in producing thunderstorms in places you would not normally see them. Thunderstorms going up in the middle of air masses. And now lightning. And there has been a lot of conversation about this picture. You can see this picture if you Google lightning on Google Images. This usually comes up near the top. It is not, as far as I know, photoshopped. It's a real picture looking toward the west, toward a setting sun, and with cloud-to-ground lightning in the foreground. Well, there are a bunch of different types of lightning. There's the most common type to us, and that is cloud-to-ground lightning. There's intra-cloud lightning within a cumulonimbus cloud, and then there's also inter-cloud lightning, which goes from one cloud to another. Basically, lightning is just a discharge of static electricity. So, how does lightning form? Where does the static charge come from? So it's hard to get inside a thunderstorm without disturbing the field, and it's not a safe place to be anyway. So a lot of this is theoretical. But what you see on the left is a magnified image of something called Graupel. Graupel looks like a snowflake, but it's been covered by supercooled water drops that are flash frozen on it. That's what Graupel is. It is a form of solid precipitation. And so within a thunderstorm cloud, we have what? We have water drops, we have ice crystals, we have supercooled water, and we have water vapor, all in this mixture. And as snowflakes begin to become covered by supercooled water, frozen onto them, they are carried by the updraft, they're carried upward. And they meet uh, ice coming down, and there are collisions. And you can see this in the little GIF graphic on the right, uh, as there are collisions between the grapple going up and the sleet particles or ice balls coming down, and the ice balls strip electrons off the grapple. And so the ice balls carry negative charge down. Meanwhile, the grapple carry positive charge upwards, and you get what is called charge separation. Now, I would invite you to watch on your own the video that the link is there with the word lightning. It's a National Geographic video clip that shows super slow motion of lightning as it happens. Please watch it. It's great video. Okay, so we have separated charge. We have negative charge near the bottom of the cloud, positive charge near the top. Well, what happens next? Well, all that negative charge near the base of the cloud is enough to induce a charge in the ground. Like charges repel. I think you probably know that. Unlike charges attract. And so electrons in the ground run away, leaving a net positive charge in the ground. This is called induction, electrical induction. And so now we have positively charged ground. Now we have the next graphic, which shows the step leader. Okay, what is happening here? Well, what's happening is that the base of the cloud becomes so saturated with electrons that some of the electrons begin to leak. They leak down a conduit called a stepped leader. So the electrons are finding their way toward the positively charged ground. And they reach a point where they're very close to the ground. And what happens next? It happens so fast that we can hardly see it. But it's called the return stroke. And so I'd like to compare this to what happens at a traffic light. And I think what I'm going to do is save this for our class discussion, because there will be a lot of questions about what happens at a traffic light. If you're backed up at a traffic light in heavy traffic and the light turns green, but you're not at the beginning of this pack of cars, you're way back waiting. Do you go right away? I don't think so. We're going to talk about that more in our discussion. So really the question is, does lightning strike down from the cloud or up from the ground? Wait for the discussion. I think you'll find the answer to be very interesting. Finally, lightning hits the ground. In the soil, we have water, which is electrically conductive, has electrolytes in it. And to be hit by lightning is not necessarily to be hit directly by lightning. You can be standing on the ground near a lightning stroke and still get hit by a current within the ground. Now, especially dangerous in a thunderstorm are what we call positive flashes of lightning. And these occur when the anvil, remember the anvil is way up there by the tropopause, it becomes positively charged. And that produces, by induction, a negative charge in the ground, and a positively charged step leader develops. Now, it just so happens that positive lightning still involves electrons. It still involves the movement of electrons. But this kind of lightning is much more dangerous than normal lightning. Not that negatively charged, the normal lightning is not dangerous. It is. But positively charged flashes are definitely the most dangerous to watch out for. Well, what about thunder? How does thunder occur? Well, lightning is hot. Well, how hot is it? To say it's hot is an understatement. Much hotter than the surface of the sun. And because it is so hot, the air around the lightning stroke is flash heated. That is, it undergoes catastrophic expansion. And this produces the bang of the thunder. The shock wave propagates out in all directions. But why then is thunder most often heard as a rolling and rumbling sound rather than a single clap of thunder? Well, that has to do with the difference between the speed of sound and the speed of light. If you look at the left-hand illustration, there's a little house on the surface, and the person in that house is seeing the lightning stroke all at once because light travels at 186,000 miles per second. But because sound travels so much more slowly than light, that the person in the house hears the thunder from the nearest part of the lightning first, and then from the part of the lightning higher up toward the cloud. And so what that person hears is a rumbling sound rather than a single clap. Now, the farther you are away from thunder, the lower the sound gets. Just like when somebody is playing their music really loud, you hear the bass farther away than the rest of the sound. The bass travels faster, and so the lower pitches of the sound travel faster than the high pitches. And that's why thunder sometimes sounds like a very low-pitched rumble and roar. Well, things get really bizarre when you look at thunderstorms from the standpoint of what goes on above them, because the lightning inside and below the thunderstorm is just part of the story. Above the thunderstorm, it was discovered not too many years ago by orbiting spacecraft, by astronauts riding in the space shuttle and the space station. They began to see and detect these emanations that have strange names like sprites and elves and jets, gigantic jets. This represents energy release that is far greater than anything released by lightning traveling from cloud to ground. And so there is an electrical connection between the top of the thunderstorm cloud of the tropopause and all the way up to the thermosphere. Not a whole lot is known about this right now. This is under investigation. As we mentioned near the beginning of the course, The mesosphere is very poorly understood. The thermosphere is very different from the rest of the layers, having ions and electrically charged particles that carry all of this energy. A very strange place indeed. So that leads us finally to lightning safety. Lightning safety is a big deal. It's a very big deal. It's a big enough deal that I am asking you, no, I am pleading with you. I'm telling you to please look at this website. Study this slide. Find out where it's safe to be and where it's not safe. And I will say this right up front, that there will be a question on the final exam having to do with lightning safety. You absolutely have to know that. I do not want to see any one of my students standing under a tree during a thunderstorm. It's the most terrible place to stand. So you see a list of safe places and a list of unsafe places to stand. I think one of the more surprising things is that if you're at a picnic, don't think that standing under a picnic shelter is going to give you any protection. You need to get inside a hard-topped car, not a convertible, not a ragtop, a hard-topped car, windows up, closed. Golf clubs, golf courses, being in golf carts, terribly unsafe. Get away from the golf course. Get back to the clubhouse. Get in your car. Get in a closed room inside the clubhouse. Don't try to ride it out on the course. Shut down your computers. Lightning can do serious damage to technology. Shut everything down. Corded phones, hang them up, get off the line. But you can talk on cell phones. Cordless phones, cell phones, okay. Corded phones, anything that connects you to the outside, get off it, okay? Out of the shower, out of the tub. Remove yourself from all of that. It's really, really important to do. As you can see from this graphic, 54% of all lightning-related deaths happen outside in the open. Get out of there. 23% under trees, 12% on the beach or in boats. If you're on a lake in a rowboat, get to shore. You are the tallest thing on the lake. Get away from there. Farm equipment and others, even standing next to an open window, has its risks. So, if you hate lightning, you're not going to like Florida. There is more lightning in Florida than anywhere else in the United States. You can see along the Gulf Coast also, and there's a little bit around the Tidewater in Virginia. Definitely an area where you have to watch out for cloud-to-ground lightning. Notably in the far northeast and in the Rockies and west, there is less cloud-to-ground lightning incidents, but not zero. Please understand that lightning can hit anywhere. And I close with this photo. There are such things as bolts out of the blue. This is an example of a lightning stroke coming horizontally out of a cumulonimbus cloud and striking literally miles away from its origin. I think the record that anybody knows of is about 14 miles for a bolt out of the blue. You don't have to be under a thunderstorm to be hit by lightning. At the first sound of thunder, seek protection. Don't wait until it's close. And wait for a half hour after the last thunder is over. Half hour before you go out and resume any activities out in the open. Then, and only then, will you avoid the potential dangers of the bolt from the blue. Thank you, and we will talk about this in our discussion.